screen. Okay, today we're going to be talking about a little bit about like statistical and machine learning models, and this is gonna be like maybe a little scary. So this is mostly just getting familiar with this stuff. I don't think this like I wouldn't expect a data analyst to know this stuff for an entry level position by any means, but I think getting a little bit familiar with it and like seeing it, then one day if you do want to go into a more advanced analysis, it's it's the more you see it, the less scary it becomes. Definitely very intimidating when you first see it, but we're just gonna go over some examples, kind of see what's possible here. And then we're gonna do like a small example project, kind of continuing on with what we've done before, but not like you don't have to apply this in your project. This is just exposure to these libraries. So don't stress, okay?
Okay.
We'll talk a little bit about, we'll talk about what did I say? Yeah, we'll talk about statistical models, machine learning models. Then we're gonna go through some notebooks in Anaconda Cloud, and then we're gonna do a little example. So some of this we've seen a little bit in the previous notebooks. So like traditional statistical models, we have linear regression used for predictive analysis to understand relationship between dependent and independent variables. So like, for example, like in real estate, we can help to predict the price of a house based on different features, like the number of bathrooms, bedrooms, location. So if you have those data, like you have the model trained where we've been able, but like we'll feed in the features of like, oh, this house or like all of these houses in the area have these features and this is the price that is sold for. Then we can kind of predict, oh, here's a new house that we're about to put on the market. Based on these features, what will be the prediction? So there's like an example in real world where we could be using this. And there's like a ton of ways that this could be used. And it doesn't always make sense, and then if it doesn't make sense based on the analysis, you would pick a different approach there. Some of the libraries, it's, and I want to say this is, I don't even know how to say this, Skykit learn stats models. Then logistics regression used when the dependent variable is binary in nature and predicts the probability of categorical dependent variable. For example, in a medical field, logistic regression can be used to predict the likelihood of a patient having particular disease based on like the observed characteristics. So age, sex, body mass, various blood test results. You could use logistic regression to predict whether they are a high-risk patient developing diabetes or other, like, I don't know, maybe cancer. But yeah, developing diabetes based on the insulin levels, obesity status, and family history of diabetes. So those are just kind of like the different characteristics, different features that we will train the model with from historical data. And then when we have a new patient, we're only going to feed in those characteristics, like, oh, like this is their insulin level and this is the obesity status, and then the model is going to predict whether or not they are going to develop diabetes or like what the risk percentage is there. Then there's something called ANOVA, so analysis of variance, used to analyze the differences among group of means in a sample. For example, like agricultural scientists who wants to determine the effectiveness of different fertilizers on crop yield. So they could set up different experiments with different fertilizers and then analyze what the difference was between those different fertilizers. Time series, techniques for analyzing time series data, used for non-stationary data like economic weather and stock price data. So financial analysts using time series to forecast future stock prices, market trends, economic cycles. We did a couple charts on like time series. And there's chi-square test, statistical test applied to sets of categorical data to evaluate how likely it is that any observed difference between the sets arose by chance. So example, suppose a company wants to test whether the preference of a product is independent of customer gender. They might conduct a survey where customers are classified into the genders and then testing their preference on the product and seeing and doing analysis based on that. Then machine learning models. So we all know AI and all these big language models have become big in the past couple of years. And we're going to see we've seen a little bit of this, and then we're going to do the example to go a little bit more to understand how that's being done. But basically how works is they're feeding in a bunch of data, and then based on that data, they're going to train the model to respond to certain questions based on the data. So then when new question is come in, the model will be able to respond to it. It's I think that's very difficult to actually explain how exactly that works, but I just had an example and I completely just forgot. But yeah, so for example, yeah, actually, the problem with this a lot of times, and we've seen some problems come with the GPTs, is it ends up being biased because their training data is biased. So for example, Amazon, back in the day, they tried to use machine learning and AI for hiring. So they would feed in all of their employees' resumes into the model, and then the model would analyze new applicants' resumes. But since their current employees were majorly male, majorly white, it would end up being biased toward women because there's different kinds of language that women use on their resume and men use on their resume. So that's something to be mindful if you are ever developing your own model, that if you put bad data in it, you're probably not going to get good results out of that. There's two different types of machine learning models. We have supervised learning and unsupervised learning. Examples of supervised learning models, we have decision trees. So continuously data is split according to a certain parameter. So that's kind of you can think of that as if-else statements, basically. So you're going to have data and I don't know, we're looking at the house prices or whatever. And then the first question is going to be oh, does this house have more than 3 bedrooms? And then it's going to go to the next question. And that way it keeps splitting and splitting. And then ultimately it ends up in some kind of analysis decision. And we have random forest, popular machine learning algorithm that belongs to supervised learning technique used for both classification and regression problems. And these are very heavy in statistics and machine learning, and definitely not something that entry-level data analysts will be expected to know. Support vector machines, supervised machine learning algorithms that can be used for classification and regression. Neural networks, set of algorithms modeled loosely after a human brain, designed to recognize patterns. Then we have unsupervised learning models. K means clustering. So when you have unlabeled data, it can help, you'll see like where the clusters start to appear. Hierarchical clustering, also used for unlabeled data set. And then principal component analysis, technique used for identification of smaller number of uncorrelated variables known as principal components from a larger set of data. Then we have Q-learning and deep Q network. This is even heavier into, I don't even know about these. We'll take a look at some notebooks, kind of examples of all of this. So if you do want to look at these notebooks, they are in Anaconda Learning, Machine Learning, and then Introduction to Machine Learning. So from the launcher, Anaconda Learning, Machine Learning, and then Introduction to Machine Learning. And this is where all of them are. And we're not going to get like super deep into these. Again, kind of like, you know, exposure to the stuff, seeing a little bit how they could be used. So for example, if later in your career you're like, oh, like I wonder how I could predict this better, or like what kind of analysis I could do, and you can look back and you're like, oh, I remember we used something kind of like that in class. So just having exposure, having like a little bit of the knowledge of what can be done, that's all we're going to do today. We're not expecting you to know all of this stuff. So starting with calculating residuals. And I've also added some like extra notes in these notebooks on my end, and I will also upload these to the shared drive just to have a little bit more information on what everything is and what do they do. But yeah, residuals are differences between observed values of the dependent variable and the values predicted by a model. Essentially, the error components in predictions representing the amount by which model fails to capture the data accurately. So here we'll do an example of like our data. Then we have actuals. And this is like for, I think this one we're just going to plot like a line. So we have our points here, and then if you remember from math class, we have y equals mx plus b. So that's our slope here, or our line here, and that's the relationship, or like a perfect line here for our data points. And then we can do and this one should be, this is supposed to be a code, right? No, it's not. I will see this. I've added here, like, how do they work? Calculated by subtracting the predicted values. Here's the equation for that. And then assessment of the model fit. But yeah, we'll go through, we'll get into, like, we'll look at the actual models a little more. Calculating sum of squares. Sum of squares is essential in statistics, particularly in the context of variance and regression analysis. Quantifies the variation within a set of data points. Is used to measure this discrepancy between observed data and model predictions. And here again, we have the same data that we looked at. And then doing sum of squares, it's like the variation between the observed data relative to the mean. So kind of like, and here's the different kinds. So like total sum of squares, That's the total variation, calculated by summing the square differences between each observed value and overall mean. So included the formulas here. The regression sum squares quantifies the total variability explained by the model. Sum of square differences between predicted values and overall mean. And illustrates the effectiveness of the model in capturing the information in the data. This residual sum of squares decomposition of SST. And this is just a quick overview of those. This is, we'll see here a little more what makes sense. So linear regression, fundamental statistic and machine learning technique used to model the relationship between dependent variable and one or more independent variables. Goals to fit a linear equation to observe data that describes this relationship. So to do linear regression, we're going to use the sklearn. So from sklearn.linear model, import linear regression, and then we're going to use pandas and matplotlib for playing with the data and visualizing it. So here's just a random data set of X and Y values. And we're going to put our X equals like our input variables. And this is just getting all the X values. The reason this is like this is because if we were to, we'll see a little bit later on how this slicing here is. Basically selecting all the rows and then everything except the last column. And that would make a lot of sense because like, so how we were talking about like predicting diabetes. So if we have multiple columns with, you know, their insulin levels and obesity and whatever. So those would be like the first columns that we're going to put in X. And then Y is going to be like yes or no, or whatever the predicted value is for if they're going to get diabetes. So this is just how it's just sliced a little funny here. And then Y is going to be just the last column. And this could totally just be, we could just do, this is lowercase x, yeah, X. And then this one captures Y. So that's the same thing. And this, in this data set is the thing. So with the, like, doing a model with linear regression, we call it fitting the model. So we're going to fit, so we're going to do linear regression dot fit. I'm going to pass in X and Y. And then here we can calculate. Did I not import everything? No, it did not like this. Is that what happened? Okay. Oh, because, yeah, we just want the values. That's right. Yeah. Anyways, yeah. So we get our M and V here. So coefficient and enter whatever this is. And then we can plot it. So the relationship between like X and Y, and then like the predicted, this would be like the prediction if we like, we added more X's here. So how is like Y related to that? So that's the like linear regression. We're expecting it to be linear. So key components, dependent variable you're trying to predict or explain. So in this case, it's Y. Independent variables, variables you use to predict. So again, in the diabetes example, predicting whether or not the person is going to get diabetes, that will be our dependent variable. And then all the other characteristics are the dependent variables. So the equation for this, and then I just put other things here. We'll go over all of this. Then, so this one we're not like this is actually not doing the, like we're not doing the training and testing. So here we'll do a train and test split, which I think we did one example at some point. And this is a different, yeah, we have more rows here. And we're doing the same thing. So put an X in here, Y in here. And then we're going to separate training and testing data to evaluate performance and reduce the overfitting. So you can choose like what the test size should be and what the training should be. And this one is like 33%. And what with this one, because like we already have the dependent variable here. So what we're doing is we're going to pick, 30% or 60% or 50% or whatever of the data with the answer. And then we're going to take rest of the independent variables and see how closely we can predict the correct answer with the model. So that's yeah. So model equals linear regression, and then model.fit, we're going to put X train and Y train in here. So the training sets, then the result, and this is giving us the like accuracy of it. So with 99.4% accuracy, we're expecting this to be able to predict the Y value based on the training data. And then we can, and this one is very, because the points are like so close together, like there's not a lot of outliers. That's why like the accuracy is very high, like on this data set. And we'll see an example of this. Well, it's actually this one, I think. Yeah, I think I'll just let you guys look at these by yourself. Basically, it just has you fill in the question marks here. And I also broke these out a little bit, so I'll upload these ones as well. But like here, it will be like MX plus B, I think, yeah. And this is like actual Y predictor or something like that. But yeah. And this one, yeah. Oh, no, that's not the one. This is the one that I'll try to. Yeah. So it just has examples of what we just talked about. The logistics regression. So like we talked earlier, used for binary classification. So this is actually better example of the whole diabetes thing. So like models the probability that observation falls into one of the two categories based on one or more predictive variables. So unlike linear regression, logistic regression outputs probabilities by applying the logistic function to linear combination of predictors. Same thing. So this one we're importing logistic regression. See your data. So here we can see Y is like binary, so it's either 1 or 0. Same thing here. We can plot the values. So we see Y is either 0 or 1 here. And this is just like random data, like it's not proper data or anything like that. Can do the coefficient values and then plotting it. So here, this is the like predicted here, which like kind of makes sense because like we can see as X grows here, there's like a little bit of, you can see the more it grows it gets here, but then again, there's a lot of points earlier here. So whether or not this is a good predictor is questionable. But yeah, so dependent variable, logistic regression is binary, meaning it only takes two positive values, 1 or 0. It could also be like pass or fail, win or lose, healthy, sick. Independent variables. So those are the whatever other would be that we already have. Include the equation here. So yeah, this one will be, and we'll look at that later, a little more clear example. So that is, yeah, that example was just like a 2 columns, or like one independent variable and one dependent variable. But we can obviously do it on multiple columns. So here we're going to, so here we have like the good weather indicator. I think this is what it stands for. So whether or not, based on these 4 columns, would it be good weather or bad weather? And that's what we're going to do here. So X is going to be all the values except the last value. And then Y is going to be just the last column. So we're going to create our model, logistic regression, and I didn't run this. Yep. And then coefficient values. So we're here, we're going to feed in a new row. So based on, so we have rain, lightning, cloudy, temperature. So not rainy, not cloudy, or no, not lightning, cloudy, and then temperature of 76. Predict the probability that this would be good weather. So if we do prediction and then, so represents the probabilities of each class of the target variable. So 98% probability that given weather conditions, no rain, no lightning, cloudy, and temperature of 76 corresponds to not good weather. High probability suggests that under these conditions, it is very likely that the weather will not be considered good. And then this is 0.015 probability that the same conditions indicate good weather. So low probability indicates that it's very unlikely that the weather will be considered good under these conditions, which is, yeah, so we don't have rain, no lightning, a little cloudy, good temperature, which is, I feel like that's still pretty good weather. So I don't know what the data set is telling us. Does this make any questions on this? And again, this one could be like what I was saying earlier, housing, medical, whatnot, to predict. Oh, okay, shut down. Too many kernels. And then there is confusion matrix, ROC, receiver operating characteristic curve, and AUC, area under the curve, used for classification problems. And these also come from the sklearn. We're using the same data set, doing the same thing here. And we're splitting up the training and testing data, leaving out 1/3 of the data for testing, and then doing a logistic regression. So this is the same thing that we were doing earlier. But what we're going to do after this is we're going to evaluate the test data set predictions in a confusion matrix. So we want the diagonal values from top right to top left to be high as possible, and then other ones we want them to be 0. And this is what this would say that like our logistic regression, like the model performance is perfect if these are 0. So this one shows that the model has done really well. It's identified all positive and negative cases correctly. And then we can also look at the AUC, which is the single number to compare like the consolidated performance. So what this means here, so confusion matrix is a table used to describe the performance of a classification model, like which the true values are known. And then, so up top, we have true positives. So the first, this one here, true positives, number of correct predictions that the instance is positive. Then we have true negatives, number of correct prediction that instance is negative. So kind of like whenever you do like a research study and you have like your hypothesis, so like you have like your null hypothesis and whatnot. We have false positives, number of incorrect predictions that the instance is positive, known as type 1 error, and then false negatives, number of incorrect predictions that instance is negative. So actually, I think this is I don't know if I set the right number. I think it's true positives. Yeah. And then ROC curve, graphical plot that illustrates diagnostic ability of a binary classifier. Then there's true positive rate and false positive rate. We don't have an example of that right here. But the AUC, area under the curve, provides an aggregate measure of performance across all possible classification thresholds. So essentially tells us how much the model is capable of distinguishing between classes. The higher it is, the better the model is. Or predicting zeros as zeros and ones as ones. So yeah, basically better. So when it's 1, that's good. Let's see. Yeah, exercise. Again, this is just filling that in. And we'll talk about these ones. These ones are a little like up there, but we'll look at them. So naive Bayes, I think that's how you say it, hopefully. So probabilistic machine learning model that is used for classification tasks based on the Bayes theorem and naive assumption that the predictor variables are independent of each other given the target variable. Simplicity allows the model to be extremely efficient, particularly on large data sets. And here we're using this on like classifying whether or not email is spam. So here's some spam emails and then spam indicator. So this one vector is a message in each email by counting each word's occurrence and break it up into input X and output Y columns. So all of the words are, so we get 74. So it's basically counting how many times the words occur there. We're going to do our train and test data set on 1/3 data again. Then we're going to do model equals multi-nominal NB, fitting it. And then the score is going to be like the accuracy. So 75% accuracy, we could filter out spam emails based on this. And then we can do the confusion matrix here as well. So it's not perfect. And then I added all of this here. So usage, very popular in text classification, spam filtering, medical diagnosis. Very efficient, simple, good performance. Disadvantages, assumption of independent predictors, strong and often unrealistic assumption that can limit the accuracy in real world applications. And then data scarcity, the probability of 0 can occur if categorical variable has a category in the test set which was not present in the training set. so getting zero frequency. But there's ways to deal with that. Let's see. This is pretty much the same thing. We'll look at decision trees. And we're looking at the weather data set again. And this is very large. Using 1/3 of the data for testing, same thing as before. And then we're going to do decision tree classifier. Max depth is how many levels of decisions. And then we can look at, so this one says perfect accuracy. And we can look at the confusion matrix. And yeah, that looks good. And this one doesn't really tell us much, but it's doing the same thing, like predicting the good weather or not. Based on, so it's basically like we'll take all of them and then determine like, oh, is it whatever rainy or is it lightning, and it just keeps splitting until it ends up in a bucket determining weather. I wonder if there's like a visual, something that visualizes that. That'd be cool to see. Random forest. Using the same data set. So this is kind of like we're using different models on the same data. So that's kind of like you could test different models, see which has the like highest accuracy for whatever you're trying to do. And this one's random forest classifier with 300 trees, limiting depth to 10 nodes, and allowing maximum 4 features. Confusion matrix. So this one, random forest and the decision tree, they give the same accuracies as each other. Talk about neural networks. So this data is, we have 3 columns, red, green, blue, so RGB, so colors. And then we're going to determine whether or not, I think this is whether or not light or dark font should be used. I'm assuming. So based on what the color is. Do the same thing here. So fitting a neural network, classifier, middle RELU function, 3 nodes, 1 million, 100,000 iterations. And this is MLP classifier. And then we can get confusion matrix is here, pretty good. Test score, 99%. So if we were, so you could feed in a new RGB code basically here, and it would tell you like whether or not, I want to say it is like whether or not you want to use dark or light font. Kind of like in UI, UX design, there's like rules on like the contrast level that you want to have between text and the background, and spacing between things, whatever. So you could kind of use this to do that. Or that's probably what it uses. And oh, this one's like, I think this is doing, okay, so handwritten digits. And I think we're trying to determine, assuming the class, would it be what digit it is? And this is a huge data set. And this, yeah, this takes long to run because it is a huge data set. See if it gives us out what it gives. Maybe it'll work. Dun, dun, dun. We'll come back to it. Hopefully it'll run. Yeah, let me look at this. Oh, it says it is. Come on, you can do it. Okay, there we go. I think what it's doing, it's like display heat map for each digit's character weights. Oh yeah, this is numbers, that's right. Not handwritten digits. So I think it's trying, like based on the pixel, so it's looking at pictures, and then based on where the pixels are placed, or you know, the color of it or the contrast of it, it's gonna try to figure out what digit it is. Let me look at this and handwritten digits. So like here, let me read this. It's like feeding in all of these. It's going to try to figure out some Chinese, which I don't read. So like here, it will be able to predict. And that's like if you've ever, I think some, like for example, I use GoodNotes on iPads, and that one you can handwrite and then it converts it into text. So most likely on the background, it uses something, a model similar to this, that is, you know, it has a date, like a trained data set has been fed into it, like of all these different kinds of handwriting, and it will determine whichever like pixels match the closest to be able to determine what letter or digit or character you meant to write, because everyone's handwriting is different. GoodNotes, they also have, you can like contribute to their data set. So like it'll tell you to write, like it'll give you a sentence for you to write. And that one, they're just getting free data for their data set to be more accurate on that. But that's, yeah. I think these ones you can't really. I can't really make much out of this, but I'm assuming the model can. Like that one's probably a 1. But I have no idea what's going on in the rest of these. But that's an example of how you would use all these different models. Any questions on this? And I am not a machine learning engineer, and I also not a statistics person. So a lot of this is a lot for sure. But just to have some exposure to this, because it does become less scary over time. Like when I first saw this, I was like, I don't understand any of this. And now I'm like, okay, like I get it between, ugh, gosh, kernels, between the like training and data set, the training and testing data set and what's going on with it. So mostly just exposure. We're gonna do a break and then we'll look at an example. We'll do till 7:10. Okay. If you hear somebody whining in the background, that's my dog because she's not getting attention. But she's fine, I promise. Okay, we're gonna do a little example. Basically, we're gonna do what we've done before. So, put our data, do a little bit of EDA, and then do a couple like machine learning examples or model examples. Bunch of things that we're importing here. Got our NumPy, Pandas, Seaborn, Matplotlib. Then there's Tablet that just makes showcasing some data a little prettier. We're going to be using California housing dataset from sklearn.datasets. So sklearn, they have like within that library, they have some datasets that you can use, and you can just import them like this, which is pretty cool. Then importing logistic regression, linear regression, metrics, mean square error, R2 score, train test split, standard scalar, and then classification report and confusion matrix. Gonna load the data. So we're gonna do California data equals fetch California housing, and that's how you get the data set from there. And then putting it into a data frame. So pd.dataframe, and putting California data, columns, and then df medium house value is equaling to California.data.target. So we were to look at like, we could just look at California data. Let's see what this shows. So this one has, it's, okay, ma'am. It's a dictionary of things. So we have data. So over here. And then we have target. And there's other things, frame, target names, feature names. And here's also a description of it. If actually, if we print this out, is this any prettier? Potentially, maybe. Nope, it's not. But yeah, so that's what's there. So we're gonna do what we usually do. So df head, let's take a look at. So we have, and I also have the column key here. So actually, let me move this up actually. So so we have medium income in block, how medium house age, average number of rooms, average number of bedrooms, population, block population, average house occupancy, house block latitude and longitude, and then we have median house value. And then we can also look at what we usually look at. So let's see, df describe. We can get some statistics here. We can already see from the counts, if we were to look at df.info, whether or not we have any null values here. Let's see, 20,640 non-null. That's the total of entries here. So we have no null values. Every single column is a float, and that seems appropriate here because they are all decimals. Or sorry, these are all decimals here. Yep. Which we could have. The column key. So yeah, don't really have to check for null values, but we can. Is null dot sum. Just confirming no null values. And then also we already looked at the df.info for data types. We don't have to convert any of these. Let's look at some dealing with outliers. So there's something called interquartile range, IQR, that we can use to remove outliers. So we're going to do Q1 equals df dot quantile, quantile dot 25, and then Q3 equals df. So this one's getting like beyond the normal distribution. And then we're going to see Q3 minus Q1. And then we're going to do in, like, we'll call this df clean from df. For df is greater than Q3, we need Q3 plus 1 plus and any axis equals 1. And then we can look at how many, let's say, df shape. We had 20,640, and then we can look at df clean shape. So we had about, what, 4,000? We actually look at this. We do df shape 0 minus df clean shape 0. So about 4,320, 4,328. We're kind of outside. We're outliers in the data set. Feature engineering, we could do something like whether or not the house value, like the median house value, would be considered high value based on like the median of the full data set. So we can do df head. So we'll do like the threshold equals df clean and median house value and do mean, and then we'll do high value, and this is just going to be a we don't need this one. This is just going to be like 0 or 1, whether or not it's considered high value. So df clean mid house value greater than the threshold, and as type int. What's in here? And let's see, df clean. Oh, this good clean. Yeah, there's some complaints about this. We can do it that way too, but location 1. Yep. Dot lock. Oh no, we can just do, yep. Oh yeah, I think either way, yeah, that works. So we get here our extra column, whether or not it's considered high value. Any questions so far? This is what we've been doing, kind of what you expect to do in your project, you know, a little bit of cleaning, whatnot. potentially dealing with outliers, feature engineering if you want to. Let's look at the distribution of the original data set to see like what the outliers actually look like. So we can do Seaborn SNS, his plot, df med house value. Okay, true. Equals 30. So here we can see there's like pretty good over here, and then there's some that are just way out of here. So if we were to look at this for the clean data set, df clean, we see those outliers removed from there. Looks better. So let's assign, we're just gonna assign df clean dot, and remember we want to do a copy, so the with the whole memory address thing. So df equals df clean copy, so we can just keep referring to df. We don't have to do this, we could just do df clean, but it's just less typing. You can also look at the correlation matrix. So if we do a PLT figure, fig size equals 8 and df core, oops, Seaborn key map correlation matrix, annotation true, and then we'll also do cmap equals plt cm loose for the color. And here we can see, let me zoom out a little bit, maybe make this a little smaller. Do 6 by 6. Oh no, that's not good. So looking at like what have like high correlation here. So obviously median house value and then high value, since we feature engineered high value off of the median house value, these ones obviously have a high correlation here. So the median income correlates with the house value and high value. Average rooms with income. Nothing else has like a huge correlation. Okay, so let's look at, we'll do a linear regression. So let's look at df head, let's see what we comes. So what we want to do here is predict like the median house value based on these columns. So we're going to, another way we could do like the slicing, we could do x equals df drop, and we'll drop the last two columns, and then high value x is equals 1. So we're setting x to be everything except these last two columns. This is a different way of slicing it. And then y is going to be just the median house value. Actually, drop these two. Yep. So trying to predict the median house value. We're going to split the data set to test the training. We're going to be using a scalar standard scalar. And that's just how to explain standard scalar, just the industry's go-to algorithm. It standardizes the features by subtracting the mean and like scaling them to unit variance. So to the dividing values by the standard deviation. Scalar fit transform x, and then splitting it x train, x test, y train, y test equals t train test split. Putting in our data, x scaled, y test, we'll set this to like 20%. And then there's also random state is a parameter that determines how it randomizes the, like how it chooses the split. So by setting this, we can always get the same split. If you wanted to get a different split every single time, you don't have to set this. But if we want to use the same split for all of this, so we can set it. And I don't know why people use 42. That's just what people do. And I have an error somewhere. Oops, this one is a B.2. No, 0.2. Okay, so we have our, to the model. Model equals linear regression. And then we're going to do model.fit x train, y train. And we just get linear regression. Then we can take a look how accurate this is. So y pred model dot predict based on x test, and we'll do mean square error. So where that is the average squared difference between the estimated values and the actual value. So we want a low value here. Mean squared error, y test, y pred, and then we'll also do the R2 score. R2 equals R2 score, y test, y pred, and that one provides a measure of how well the outcomes are replicated by the model based on the proportion of total variation of the outcomes explained by the model. And then we'll print this out. Let's see. Let me see. Print. See. R2. So we have 31%. So it's like relatively low. So suggesting that the model's predictions are reasonably close to the actual data. And then approximately 64% R2 score. So about 64% of the variance in housing prices can be predicted from the features, which is a decent score. Not the best, but it's a decent score. We can also visualize this, like visualize how, like the performance of the model. We do PLT scatter, y test, y pred, PLT plot. X label actual median house value PLT Y label predicted median house value. We'll put the title, make it fancy. Actual versus predicted. Here we can see how well the model is predicting this. So this is showing the relationship between the predicted and the actual values. And we can see that's pretty good based on the scatter plot, since the points are mostly concentrated around here. There's some outliers, but yeah. And this one kind of, like, I think it matches up with, this is saying 64% here. So I think that's pretty accurate representation of that. And we'll do a logistic regression example. So we'll do the same thing here, except we're going to do high value. So this time we're going to try to predict the high value. And the reason we're not including the median house value here is because we use that like to determine the high value. So we want to use rest of these to see if based on those features we can predict whether or not this will be labeled as high value or not. Do the same thing here. And this is the same thing. Model equals, but except instead of linear regression, I'm going to do logistic regression here. X train, Y train. And then we can evaluate this. We do Y predict, Y pred model dot predict X test confirmation matrix. Oh, confusion matrix, not confirmation, confusion matrix. Y test and Y pred. Then we can do a classification report. With Y test, Y pred. And then output to dict just means it's going to be a dictionary. Easier to access things here. And we'll print this out. This is where the tabulate is used, just to make it easier to read. So predicted low, predicted high, table equals tabulate. Oops. High. Table F and T. And then we can print this out. Headers. There we go. So this is what we were looking at earlier in the notebooks. So we want these two to be high as possible, and then these ones be low as possible. So true negatives, these ones have, since the training split has changed. Number of correct predictions, predict the low, actual low. Number of correct predictions as instances, not a high value house. Then false positive, actually low, predicted high. Number of incorrect predictions that instance is high value house when it's not. False negatives, actually high but predicted low. Number of incorrect predictions that instance is not a high value house when it is. And then true positives, actually high when it's predicted high. Number of correct predictions that instance is the highest value house. So that's like pretty good. Then we can also look at, we'll look at the classification report. And this is accessing the, if we were to look at, let's see, if we look at the class report just like this, so we can see here 0, 1, then we have accuracy, macro average, weighted average. And each one of those has a dictionary in there. So I'm just accessing these from their call. And this is just a way to like make your notebook prettier, make the information easier to like read for other people, for you too. Start. We're getting everything else except accuracy here. This one's we're getting the values. Recall F1 score for each one of these. And then we're going to do headers equals class precision. They call F1 score support. And then we're going to print tabulate or table. We are missing something. Table value missing here. There we go. So what does this tell us? The precision, the ratio of correctly predicted positive observation to the total predicted positives, measure of classifier's exactness. Low precision indicates a high number of false positives. So precision for 0 for non-high value, 84%, or this is actually 86, and about 81% here for high value. Recall, sensitivity, ratio of correctly predicted positive observations to all observations in an actual class, Measure of classifier's completeness. Low recall indicates high number of false negatives. So recall for 0, 80, this is also 86, 81. F1 score, the weighted average of precision and recall. Therefore, this score takes both false positives and false negatives into account. It's a good way to show that classifier has good value and both recall and precision. So basically just a combination of these first two. Then support the number of actual occurrences of the class in the specified data set. So we have 1,688 zeros and 1,575 ones, which, well, actually 1,885, 86, 89, sorry. Then to get the overall accuracy, class report accuracy, and we'll do and text format it. So overall accuracy 84.40%. So how often is it classified correct? So true positives plus true negatives divided by the total. And then this one actually should be over here for the macro average. So from here, the macro average precision, recall, the precision, the average precision recall F1 score between classes does not take label imbalance into account, hence can be better measured when classes are imbalanced. And then weighted average is average of precision recall F1 score between classes weighted by the number of instances in each class. Very similar here. So that's something, if you're feeling ambitious and want to put any of this in your project, feel free to do so. But by no means is it expected. Any questions on this? Is any of this, it may not be clicking, honestly, because if you have never heard about this and never seen this, it's just a lot to take in. But yeah, there's a lot of different ways. This stuff is very cool, I think, and they do pay machine learning and AI people very well. But to me, it's not a huge interest. I think it's very cool, it's very important, but I enjoy more visual things. But if you're feeling ambitious and want to get into this, you will be properly financed for that, compensated. That's what I'm thinking. Any questions on this? And I'll make sure to include this in the shared folder. No questions? Okay, we're going to take a break. We'll take a break till 8 p.m. Okay. For rest of the class, I want to make sure that everyone is good for their projects. No, Melinda, you had issue with the importing the data. So just want to I'll just go over any problems that you guys have. And we can start with that. So I have Jupyter Lab opened here, but that's pretty much the same thing as if you were on the Anaconda Cloud. Works exactly the same. So if we were to do a new notebook in here, we can do, so import pandas as PD, and then we have company operations in the same folder. And I think you can even like copy the path here if it's not working just as this, then you can like copy the path and like put the full path in there. We go to df equals pd dot read csv, and that should work. So that's all there is to that one. And again, if it doesn't work, just do the full. I think actually here, are you able to? Let's see, maintenance. Yeah, so you can copy path here as well, and then use that. So if we were to do, let me do a new notebook in here. So PD to CSV. And that one's getting like the full path here. No, oh, not to CSV, read CSV. Okay, it will not do that way. It will do it that way. Okay. Actually, I think the full path, but yeah, this should work. If you're in the same folder, just getting the name of it. And I think if you were to do the full path, we need dot in this. No. Okay, the full path won't work here. So just have it in the same folder, and that will work, or should work. df.pd read CSV. And this is in Anaconda Cloud. So yeah, that's all you do with that. Do you have any other questions or anything that you wanted to go over? I know you kind of were just getting started, so, but we can go over anything.
I was just gonna pull back up like the walkthrough file that you gave us and maybe just see if something jumps out. But I think it's just going taking it step by step.
Mm-hmm.
Let's see. I guess maybe I was like looking at the data set I was thinking about using and looking for opportunities for cleaning in there. Are there specific things you want us to let Joey know how to do for cleaning, or what you want us to do for like data set exploration? Is it, kind of what you have in this example that you gave us? Is it that you just wanted to kind of run through those types of requests to just see kind of what the data has for us?
Yeah, so kind of like, so the project walkthrough that we did, so like, like looking at the shape, looking at the info, like just looking at the data types, making sure if there's anything that like seems incorrect that you want to change the data type, or then if there's no values, how should you deal with them? And if there's not no values, you can just include that you checked for them, and you could say like, oh, like if this column had null values, this is how I would go about it. So kind of like
Okay.
along those lines.
Okay.
Yeah, that's pretty much for, and then, like if there's like any columns that have zero value, like getting rid of those columns, or
Okay.
yeah, like most of the null values, and then like making sure like you want to get your data ready for
Mhm.
analysis and visualizations. So if you see any problems there, like kind of fixing those. And then if
Okay.
there aren't any problems, include that you checked for those problems, like null
Okay.
values and whatnot. So that's
Okay.
kind of like, because like you might find a data set that has already been cleaned. So there
Right.
is no null values, and like maybe all the data types are correct, but like you should know how to check for those. And I want to see
Mhm.
that you know how to check for those.
Okay.
And you could even include like, oh, like if, how do we do here? Like filling out the, like fill NA is how you would fill the null values, like anything like that. But it's flexible.
Okay.
But yeah, this one has pretty good. And then also the notebook. I included the notebook for, let's see, we talked about it on class 5. Yeah, notebook 5. Let's see, do I have my deep note open? Yeah. So yeah, like final project, this notebook is included in the shared folder.
Okay.
So just kind of whatever the steps are here.
Okay, cool.
Anyone else have any questions? I know, Rosendo, you asked about the GitHub. Did you want to walk through that again? If like maybe it wasn't clear enough how to get your notebook on GitHub. I think the easiest way, if you're using Anaconda Cloud, like you're creating a notebook here, the easiest way to put it on GitHub, because I don't think you can't do it directly from here, I don't think. But like you would want to download, like after you're done with it on Anaconda Cloud, you would download it on your computer and then put it in a folder, include the data set that you used, and then a notebook, put those in a folder, create a new repository. So how we walked through last time. And again, this step is optional. You don't have to do this, but if you want to do this, here you would create the new repository, put in a name, set it to public. You don't have to do any of these. And then they'll test. Oh, actually, let me look at sample project, this one. So like once you upload it here, I think you can upload it from here. Like you don't even have to do any of the like terminal command line stuff. You can create a, let me look at the test, hotel test. You can upload a file like this. So drag files or upload them. Let's see, we'll do project walkthrough. Oh no, yeah, we'll do both of these. So uploading these, but you have to like add project walkthrough notebook, and then commit directly to the main branch, commit changes. So this is like doing it from the UI, like not having to do any of the like git commit or doing in Visual Studio. You can upload them directly here. And then here, just by uploading it, it's going to show you the notebook. So if you wanted to share your notebook with me this way, you could, and then you can just ping me the link to it. You just have to make sure that your repository is public. And I think you can, from the settings, you should be able to change the security. No. Images. Change GitHub repo from private to public. Oh, okay, it is in a danger zone. Okay, yeah, change repository. So here you could change it to public if you had created it as private. Because if it's private, then I won't be able to see it unless you add me as a collaborator. But that's all. That's how simple it is to put on GitHub. And like we went in the notebook from Monday, if you wanted to embed it to a website, I put the code in there. Class 7. So here, just using an iframe and the NB viewer. And that's if you want to put it on your personal website or whatever. Any questions on that? It doesn't matter what you name it. You can name it literally anything. Just probably don't do anything inappropriate because it will stay on, you know, the commit history. Any other questions or problems with the project? Or anything that you guys want to go over again? Something, or like one more information explanation on? Everybody's good with the projects due at the end of, okay. It's better to create a specific GitHub repository projects. You mean like you just want to, like you can, I would say like for the way I use GitHub is you create a repository per project. But for example, some people, for example, like if you're in school, you could create one repository for the full class and then put all of your assignments in there. So folder. Yeah, so like you want to, the thing with GitHub is if you have a, so this is my like Python 101 folder right here. Hopefully you can see it, or it doesn't really matter. If I were to initialize the Git repository in this folder, it would include, like it will be keeping track of all of these folders. And I may or may not want that. Again, like if you could do it to have a Git repo that is for like this class, like you do Python 101 for spring, and that is going to include all of your assignments or whatever you're doing. And then that's your repository. Or you can just do it per project. Like you could have one for the scavenger hunt, and then you could have one for the project. Yeah, don't share all your things. So definitely like if you're using Anaconda Desktop, what you would want to do is, let's see, so you want to make sure that if you're using terminal to initialize your GitHub, and again, like even if you initialize it, it's gonna like, you can see what you have added to be published before you publish it, but just make sure that like you're in the project directory. So if we're looking at here, we'll just do like the project walkthrough, and this one already has a Git, and you'll see it here as soon as I got in here. And actually, does regular terminal do this? Not sure. I think so, maybe. New window. Okay. It does not. So highly recommend WARP. WARP, because it will tell you if there is like Git repo in that folder already. And here we can see like Git log. And what else we could do? Git. Another thing you can do is Git diff. And this one's going to show you everything that has been changed since the last commit. But yeah, you want to make sure that you are in your project folder when you do git init, and that way it will initialize the repository within that folder. And when you do git add dot, it would add everything from that folder that you initialize it in. And if you are like nervous that it's somehow going to include other files, first of all, it's going to show you what it did add. And that's why it's kind of like, if you have Visual Studio, like it's definitely more user-friendly to do it that way, because you can see what files are being added by under the stage changes. So like, for example, here, I have changes in main here that have been changed since the last commit. But then these also, so this is adding it here, and that's click that stage. So like if I were to commit right now, it would include the print hello world here as a change. But actually I've already removed it because I didn't want it there. So if I come here and plus it now, there's actually no change at all. But here we can see like this was added. So once you go and add it here, you can see everything that's going to be added to that commit. And then you're going to put your commit message and commit. And when you commit, that does not yet publish it on GitHub, but it is going to be included. Like if you do a bunch of commits right now, and then one day you decide like, hey, I'm going to publish it now, but like I removed whatever weird stuff I had, like sensitive information or whatever, it will be included in the history. So like, just be mindful of that. But you can also like revert get like commits. So if one time you committed your credentials and the next time you remove that file from the commit, it would still show up in the history, in the version control history. But if you reverted the commit where you committed the credentials file, then it would not show up in history. And hopefully that makes sense. Just lots of things. But yeah, I would use, like, open up your project folder in Visual Studio. So open like Python project walkthrough. And then here, when you go to the version control, it's much easier to control what files get committed. So you would do a commit message, click commit, and then this one would have upload. But then if you've done commits and whatnot, it's going to be synchronized. So what it would do is it would pull all the changes that are on GitHub in case there were other changes that you have pushed. So it's just going to check them, make sure that everything's synchronized, and then it's going to push your changes on GitHub. That's everything clear with that. Any other questions on the GitHub? Again, not needed for your project. If you want to do it, I would encourage it, because again, you can get it to show here, like easily. Again, like for example, my resume, I have my GitHub linked, so like anybody can go look all of my public repositories. So, but you could also, like, if you put like, oh, like ODSA Python 101 class on your resume, you could include the GitHub repo, like link to this project. Like if you explain like, oh, this is a project that I completed, and like, here's a GitHub link to it. And if you include like direct to the notebook, they can go and look exactly what you've done here. Versus going to like, I mean, you can do a direct URL anywhere, but like as long as it's online, you can do it. But GitHub, it makes it very easy to do that. Any questions on that? Is that clear how to do this? If everything fails, just upload them directly from github.com, and that still works. Any other questions? And my dog has a lot to say today. Hey. Okay, well, I don't have anything else for you guys today, because I wanted to make sure that there's time for any questions regarding the project or anything that you guys wanted to review. The final project is going to be due end of the week by Sunday. Then Nate posted about there is going to be like a little graduation ceremony type of situation. I will not be there because I live in Florida, and I also will not be in the US on that day. But maybe one day I will come visit Omaha. And you will get certificates if you've satisfactory completed this course, which means pretty much attending classes and then doing the final project. Those are like the major things. Yeah, that's it. I probably will be teaching another different class sometime in the future. If you guys are taking a different class sometime in the future, we might meet again. And I will still be available on Slack for the rest of the week for any questions on your project. So feel free to ping me. I'll make sure to upload all these files. If there's any files that I have not uploaded that you were expecting me to upload, just let me know. And I'll make sure that you guys have everything. The recordings are going to be on YouTube. I think Nate said that they're there for like 3 years. So for review, but yeah, if there are no any other questions, we can end class a little early today. Waiting for y'all's final projects. All right. Have a great night, everybody. And ping me if you have any more questions.